Okay, for 5.4, we have step 1 where we see H2 plus ICl, and that happens slow. And then we see step 2, HI plus ICl, and then we have both of them, we have replacement reactions. Okay, and so which of the following represents the overall chemical equation for the reactions and the rate law for step 2? So step 1 happens slow, step 2 happens fast, and when we stack them, we get H plus ICl equals HI plus HCl. And so what happens is now we're going to cancel everything on both that are on both sides. So HI is produced on step 1, but it is also in step 2, so it cancels. And is there anything else? That's all. So we're left with H2 plus 2 ICl, plus 2 ICl, because we have this one too, turns into HCl and HCl here, so we'll write 2 HCl plus I2. That's the overall reaction, right? And then if we're looking at the rate law, we have rate law is K, and then we have HI and ICl, because HI and ICl are what lead to the reaction for step 2. Those are reactants. Okay, so the overall reaction was H2 plus 2 ICl turns into two HCl, so it's not A. This one has the H2 plus 2 ICl turns into 2 HCl plus I2. It has this. It also, but it doesn't. It has this in here, so that can't be it. And then here, the overall reaction is H2 plus 2 no, but this one doesn't have the 2 here, so it can't be this one. So I'm assuming it's going to be D, because 2 ICl plus 2 HCl plus I2, and the rate law is K HI plus ICl, so it's D. Okay. Kind of want to zoom out, but I want you guys to be able to see this clearly. Question number 2. A two-step reaction mechanism is proposed for a gas phase reaction as represented above. So this is a gas phase reaction. Which of the following correctly identifies both the chemical equation for step 1 and the rate law for the overall reaction? So they don't give us step 1 at all. So they want the chemical reaction for step 1. So we kind of got to work backwards. Well, the overall has CO2, and that is there. But there's no NO here, so there needs to be NO here. And then CO here and CO here, and then NO2, but there's no NO2 here, so there needs to be NO2 here. And so there'll probably be an arrow here too. And so now, how are we gonna take 2NO2 and end up with NO and CO2? Let's, try, because NO3, it needs to get canceled, right? Because it doesn't end up in the overall. So here, NO3 needs to end up on this side. Right? And here there is 1 oxygen, and here there is 3 oxygens, so total of 4 oxygens. But here there's only 2 oxygens, and here there's 2 nitrogens. So if we put just whatever's left over, we get NO2 plus NO2 turns into NO plus NO3, right? And that kind of accounts for this NO3 getting canceled because neither of them show up here. And what's left over here is NO2, and this NO2 will probably get canceled. So what's left over is this NO2 ends up here, this CO2 ends up here, this NO2 ends up here, and this carbon monoxide ends up here. Okay, I don't know, can we just solve the problem based off of that? 2NO2 turns into NO and NO3. Can we just solve the problem off of that? Yeah, that's A. There's no other answer that has that. So yeah, the equation for step 1 is this. And the rate law is this, right? Because there's this is what leads to this. So it's just NO2 squared. So it's A. Okay, question number 3. NO2 and O2, not NO2. I'm sorry, I guess I'm having a bit of recency bias. NO and O2 react to form NO2. The rate law of the reaction is NO2 second order and O2. The rate occurs in a single elementary step that is a 3-body molecular collision. Which is the step for the elementary? So we know the rate law, NO2 and O2. The problem here is that the reaction says it's going to be a single elementary step and a 3 element collision. That means that this one has to have 2 NO molecules and 1 O2 molecule, because those are those are what's in this is like the recipe, right? This is what's here. We're gonna need 2 NOs and 1 O2, right? Because of this. So the only answer that I see that has that is B. Yeah. And form NO2. Here it forms NO2 as well, but here it tells you everything that you need. You need NO, 2 of them. Here we go. And we have O2. Here we go. Moving on. Question number 4. The reaction between NO2 and CO to produce NO and CO2 is believed to occur via 2 steps. The rate the experimental rate law is NO2 squared, which makes sense because if you look at step 1, that's the thing. So write the reaction for the overall reaction. Oh, this is so easy. We just cross out everything that happens on both sides. So this NO2 goes because of this. This NO3 goes because of this. This is a NO2, there's nowhere else to be found. This is a CO, that's nowhere else to be found. NO, nowhere else to be found, and CO2, nowhere else to be found. So all I'm writing here is NO2 plus CO turns into NO plus CO2, right? Now it says identify the intermediate. The intermediate is things that are made in one step, but they are consumed one step later. So here. Now, what was produced in step 1 was then consumed in step 2? Let's see. What was produced in step 1, but then consumed? There's only NO3 that does that. So that's the answer is NO3. Okay, and then what can you say about the relative rates of step 1 and step 2? Well, let's look at step 1. Step 1 was NO2 plus NO2 turns into NO plus NO3. So that, its rate law would be NO2 squared. And that means step 1 has to be the slow rate determining step, and step 2 must be faster. So I would say step 1 is the rate determining, because it kind of determines what can happen. Is the rate determining step, right? And step 2 is the more faster step, and step 2 is the faster step. Right? Because of the rate law. Alright, so if the experimental rate law matches one of the elementary steps, if the rate law, which was step 1, right? If they match, if you look up here, right? The rate law matches step 1. That will always make it the slow step automatically. If they match, it makes it the slower step. Okay, next question. Okay, now we're up to 5.5. Again, if you need help with the quick checks, let me know. But I'm just going to go to the practice problems. Okay, so here it says the gas phase reaction, A2 plus B2 turns into 2AB, is assumed to occur in a single step. Okay, that's good. 2 experiments were done at the same temperature inside of rigid containers. The initial partial pressure of A2 and B2 used in experiment 1 were twice the initial pressures used in experiment 2. Which statement provides the best comparison of the initial rate of formation of AB in experiments 1 and 2? Okay. The initial rate of formation of AB is the same in both experiments because they were done at the same temperature and frequency. So we know that they were at the same temperature. Here, it's the same temperature. We know they were in rigid containers, so it's not like they had any outside forces or pressure. And the initial pressure were twice. Experiment 1 was twice what was used in experiment 2. Okay, so what do they mean by this higher partial pressure? So at constant temperature, a higher gas pressure means more gas particles would have been moving around. Because they'll collide more if they're moving around more. But because experiment 1 has higher initial partial pressure, that means experiment 1, right, will have more collisions. Because when the pressure is higher, there are more collisions, they're more bumping into each other, right? So let's read the answer choices. The initial rate of formation of A and B is the same in both experiments because they were done at the same temperature, frequency, and the energy of collisions would be about the same. No, they would not be. I just finished telling you one would be greater. This is not true. Collisions between A and B would not be the same. The initial rate of formation of AB is slower in experiment 1. Why would it be slower? There's more collisions than with experiment 2 because they're the same temperature. Okay, a higher pressure would reduce the volume. No, pressure does not reduce volume to achieve the proper orientation of a successful collision. No, that is not true. C, the initial rate of formation of AB is faster in experiment 1, plausible, than in experiment 2 because at higher pressure, the collisions between A2 and B2 molecules would have been more frequent. More frequent because more collisions, more pressure, leading to the probability of a successful collision. I'm picking C, but let's read D to entertain it. I'm sorry, maybe I'm getting more confident. Could be D, who knows. The initial rate of formation of AB is faster in experiment 1, that's true so far, than in experiment 2, because at a higher pressure, a larger fraction of A2 and B2 would have the minimum energy. Pressure does not increase energy to overcome the activation rate. Pressure does not increase energy, so that's wrong. Okay. Question number 2. The reaction shared is carried out at a constant temperature inside of a rigid container. So they're at a constant temperature inside a rigid container, so nothing is leaving. Based on this mechanism, which of the following is the most likely reason for different rates of step 1 and step 2? So step 1, we have H2, we have ICl, which is iodine chloride, and then HI plus HCl, and then step 2 is HI, ICl, HCl plus I2. Okay, and at the same temperature, most likely reason for one step being faster or slower is that step 1 has a higher activation energy. It takes more energy to get started, which takes for successful collisions, for successful collisions, right? So this one is slower, and this one is faster, and so because it takes more energy, because it's slower, right? It's probably because of higher required collision energy, or you could call it activation, because those collisions activate those bonds, right? Activation energy, right? Okay, so let's read the answer choices. The only factor determining the rate of step 2 is the orientation of HI and ICl polar molecules. You guys know this from regular chemistry that that's not true. The orientation of the molecules don't matter because they're going to bounce around and eventually be in the correct orientation. So orientation doesn't matter. B, the amount of energy required for a successful collision between H2 and ICl is greater than the amount of energy required for success. That's exactly what we were saying. For step 1, which you can't see right now, but it's on your paper, requires more energy for a successful collision than step 2 does, which is why it is slower. So it requires more energy. Let's see C. C says the fraction of molecules with enough energy to overcome the activation energy barrier is lower for HI and ICl than for H2 and ICl. And that's not true because the fraction of molecules with enough energy that is lower for HI and ICl would make step 2 slower, right? Because HI and ICl are here and they're for step 2. So if it took more energy to do step 2 would be the slower step. And then D says the frequency of collisions between H2 and ICl is greater. That doesn't make any sense. Than the frequency of HI and ICl. And so that doesn't really explain why step 1 is slower. It's just untrue. So that's D is definitely not true. Because if this were true, then the collisions were more frequent in step 1, then step 1 would be faster. It's not telling you to find something that says it's why step 1 is false. It's asking you to find a reason that why is it more likely that step 1 is faster than step 1 is slower than step 2. Okay, next question. I think this is the last question, maybe. Nope. I think 6 is the last question. Totally wrong. All the way to 8. Okay, cool. So let's get to going. Okay, question number 3. All right, let's look at this. We have temperature, the number of molecules, the energy of the molecules, and the activation energy required. So the proposed rate determining step for a reaction is, and they show us, 2NO2 plus 2NO3 turns into NO3 and NO, okay? The graph above shows the distribution of energy for NO2 molecules at 2 different temperatures. Maybe it'll help me if I zoom out a little bit. It'll allow us to see the whole question. Based on the graph, which of the following statements best explains why the rates of disappearance of NO2 are different at temperature number 2, where there are less molecules, than temperature 1, when the temperature is higher. So at temperature number 2, we see that there is a greater fraction of molecules that have energy above the activation energy, right? The activation energy right here, right? And so their collisions are more effective, so their reaction should happen faster, right? Because there's more molecules available at the activation energy point than at temperature 1. If you look at the width of here, it's like, it's here to here, whereas this one, it's here all the way out here. So there's more molecules available at activation energy, and that's when things kind of can pop off, right? Okay, and so A says NO2 is consumed at a faster rate at temperature 2 because more molecules possess energy at or above the minimum energy required for a collision to lead a reaction to compared to temperature 1. Yes, that's exactly true. There are more molecules. It says there are more molecules, and we see here, based on the graph, that there are more molecules at temperature 2 that have the energy, that meet the activation energy, or above the minimum energy, which is, this is the minimum energy, right? Required for a collision, and that's why more of it, and I'm going with A. Here it says NO2 is consumed at a faster rate at temperature 2 because the molecules have a wider range of energies. That's not how this works. You just have to have enough activation energy. If wherever the activation energy is, you just have to reach it to be able to go through the reaction, right? So that's not how it works. It's not about having a wide range of energies, but it's about having enough people at the, the point that you need it to have, right? Fewer NO2 molecules have a relatively high energy for temperature 1, that is true, which favors collisions between molecules rather than the molecules and the container, leading to a faster rate of disappearance at temperature 2. This doesn't make sense. This talks about collisions with the container, right? Look, it says which high between the molecules and the container. We are not interested in bumping into the container, so that is not correct. And then D, it says more NO2 molecules have a relatively low energy at temperature 1, which increases the number of effective collisions taking place and the rate of disappearance compared to temperature 2. So it says lower energy molecules at temperature 1 increase, more effective collisions, but the problem is that's not what's happening at temperature 1. Have a relatively low energy at temperature 1. And that increases, but that's not what we're seeing here. That's according to this graph, this is not what we're seeing. So D is just, it doesn't, explain why, it just says, yeah, if it had a lower energy threshold at temperature 1, we would have more reactions happening at temperature 1. But that's not what the graph shows. Okay. Question number 4. We see Cl minus, we see ClO minus plus two H's turns into chloride and water. What effect will increasing H plus at constant temperature have on the reaction represented above? So what effect will increasing this? I saw something earlier maybe I could use. I'm going to end up wasting a bunch of time, though. We're going to increase it. That was terrible. What a waste of time. Sorry. Increase it. At constant temperature. Okay, have the reaction represented above. Oh, okay, so increasing the concentration increases the amount of collisions that could happen. The more, packages you have in your house, the more often you'll bump into one, right? The more people in your house, the more people at a party, the more people you'll bump into, right? So that's how collisions work. And since H plus is a reactant, not a product, increasing the H plus means that there will be more collisions that happen, and so that that doesn't change K. So K stays constant no matter what. The only temperature can change K. K stays constant, right? But then the activation energy does not change due to temperature either. activation due to the constant temperature. Activation energy will stay same, right? Let's see. The activation energy of the reaction will increase. That's not true. The activation of the energy will decrease. No, these will stay constant. Okay, and activation. The frequency of collisions between H plus and ClO will increase. Yes, that will increase. There's more H pluses here, and it's a reactant. These are reactants, right? And these are products. So since there are more reactants, there will be more people bump into each other. Let's look at the next question. NO plus NO3 turns into 2NO with the rate law of KNO and O3. So everything is first order. So the question here is, the reaction represented above occurs in a single step that involves the collision between a particle of NO and NO3, which turn to 2NO2. A scientist correctly calculates the rate of collision between NO and NO3 that have sufficient energy to overcome the activation energy. The observed reaction rate is only a small fraction of the calculated collision rate. Which of the following explains the discrepancy? Okay, so scientist says that the rate of collisions between NO and NO3 have sufficient energy to overcome the activation energy. The observed reaction rate is only a small fraction of the. Yeah, because they're gonna bump into each other a bunch, but that doesn't mean that they're in the correct orientation, right? Because they need to be like, molecules need to be facing the right way, right? So like NO, right, and then NO3, right? So this NO has to be able to, like, let's say this NO3 is like, right, like this, and this kind of sees it this way, it's not going to be able to react, right? So it not only do we need enough energy, so the two things that we need is the energy, right? But we also need to be in the correct orientation, right? If not, the reaction doesn't happen. But if there's enough, time and bouncing around, eventually things will bounce around to the point we can have the reaction. So the energy of collisions between two reactant particles is frequently absorbed by the collision with the third particle. Yes, that is true. This is why things keep bouncing around. But that doesn't explain his discrepancy that shows that there's a lot more reactions, collisions that happen, right? But the actual reaction only happens at a small fraction of it, right? Why is that? Because the two reactant particles must collide with a particular orientation. This is what I was talking about here. Particular orientation in order to react. This is true. Not only do they need to be having enough energy so that they can bump into each other, but they also need to be in the correct orientation. The activation energy for a reaction is dependent on the concentrations. Yes, but that doesn't explain the discrepancy. And the activation energy for a reaction is dependent on the temperature. Not necessarily. Not in the way that this question is talking about. They don't really mention how temperature would be, and it definitely doesn't explain the collision situation here. Question number 6. Here we see, which of the following best describes the role of spark from a spark plug in an automobile engine? So a spark plug